Chapter 13, Complex Reaction Mechanisms, Section 13.1, Parallel and Sequential Reaction Mechanisms. In a parallel reaction mechanism, 2 plus reactions proceed in parallel. For example, we can have 2 elementary steps, from A to B and from A to C. From A to B, we have a rate constant, denoted by K sub B. From A to C, we have a different rate constant, denoted by K sub C. So over here we have a picture that serves as an analogy. So we have a lot of water in A, and then, well, just imagine the water may flow down this pipe B or this pipe C. So overall the flow rate will be the flow rate in pipe B plus the flow rate in pipe C. So A is consumed via both elementary reaction steps in parallel. So the flowing is going on in both pipe B and pipe C. Therefore, dA over dt, that's the change of the concentration of A over time, is equal to negative kBA minus kCA. But over here, kBA is the reaction rate for this A to B. kCA is the reaction rate of A to C. So together, we have the consumption rate of A. We can combine Kb and Kc, and therefore dA over dt is equal to negative the sum of Kb and Kc times A. The production rates of B and C are different. dB over dt is just kBA. That's the reaction rate of the first step. dC over dt is kCa, the reaction rate of the second step. Well, if we look at these 3 equations, they are all differential equations, but only the first one can be solved directly. The reason is, in the first differential equation, you have only 2 variables, the concentration of A and time. That's it. But over here, in this differential equation, there are 3 variables. You have B, A, and T. Here we also have 3 variables, A, C, and T. We cannot solve the bottom 2 differential equations. However, we can solve this one because there are only 2 variables, and we can separate the 2 variables easily. So both sides divided by the concentration of A, and both sides multiplied by dt. We have this equation. Now we can integrate both sides. And then we have the natural logarithm of A is equal to negative the sum of Kb and Kc multiplied by time, and then plus a constant. We can determine this constant. If the initial condition is this, A equals A naught when time equals 0, we plug in the initial condition here and here. We'll see C, this constant, is equal to the natural logarithm of A naught. And therefore, ln A is negative Kb plus Kc times T plus ln A naught. And therefore, A is A naught times e to the power of negative Kb plus Kc multiplied by time. And you can see this A decreases exponentially, and sometimes we call this exponential decay. And it just resembles the simple first order reaction rate. Again, the concentration of A decreases exponentially in this parallel mechanism. A is A naught times e to the power of negative Kb plus Kc times T. And sometimes you can just define K effective to be Kb plus Kc. And it looks like just the first order elementary reaction with a effective rate constant being the sum of Kb and Kc. Now, given this differential equation, this differential equation, and this differential equation for the 3 species, we can sum up the 3 equations. Therefore, the first derivative of A plus B plus C with respect to time is equal to 0 in the end. So you can see all this cancel. KBA and KBA cancel, KCA and KCA cancel. That means A plus B plus C never changes with time. So if we look at this graph, assuming initially there's only A and then this water can flow into B and C, but overall the amount of water never changes. That's just another analogy for this. A plus B plus C never changes. So if 1A is consumed, it becomes either 1B or 1C, but the sum never changes. Assuming B naught is 0, C naught is 0, and then B plus C is A naught minus A, which is simply A naught times 1 minus this exponential function. And also, if B naught is 0 and C naught is 0, we know B over C is going to be, well, B naught plus the change of B over C naught plus the change of C. And if B naught is 0, C naught is 0, we have this. B over C is the change of B over the change of C. So again, the change of B over the change of C is equal to B over C. So we just need to get a ratio between B and C. And this delta B over delta C is dB over dC. Okay, because we can just integrate both sides, or we can have this delta approach 0 or approach infinitesimal, and we get this. We know dB is kBA dt from this equation. Alright, dB is kBA times dt, and dC is kCA times dt. dt and dt cancel, A and A cancel, so we have kB over kC. So really, the change of B versus the change of C is kB over kC. That does make sense, because kB and kC are the indicators of how fast A is converted to B versus A converted to C. And now we can solve two equations for B and C. One equation is this: B over C is kB over kC. The other equation is this: B plus C is A naught times 1 minus this exponential function of negative k effective t, where k effective is kB plus kC. So assuming B and C are two variables and we have two equations, we'll just solve those two equations, we get B and C. They look very complicated. B is kB over this k effective times A naught times 1 minus the exponential function. C is kC over this k effective times A naught times 1 minus the exponential function. Again, I was just using k effective as the sum of kB plus kC. And we can also verify that B over C is simply kB over kC. You can just compare the right hand sides of these two equations. They differ only here and here. kB over kC is equal to B over C. And also, you can verify by these two equations by adding up B and C. B plus C is this plus this times A naught times 1 minus the exponential function. And you can see this fraction plus this fraction is exactly 1. Now let's look at one numerical example problem, 13.1.1. In this following parallel reaction mechanism, A is converted to B, A is converted to C, A is converted to D, all simultaneously. And we have the values of kB, kC, and kD, 2 per second, 3 per second, 5 per second. Now we can calculate the concentrations of A, B, C, and D at time equals 0.2 seconds, given the initial concentration of A, which is 0.2 molar. We can also compute the concentrations of A, B, C, D when time approaches infinity. And of course, when time approaches infinity, obviously A should be 0. All of A is consumed. But now let's look at this condition. At time 0.2 second, we'll just plug in this equation. A is A naught times e to the power of negative k effective t. So k effective is the sum of kB, kC, and kD. Alright, and then the sum is negative 10. The sum is 10 per second. So we plug in all the numbers, the initial concentration, negative k effective, and multiply by time. So you can see we have 0.2 molar times e to the power of negative 2. The result is 0.027 molar. So at time 0.2 seconds, the concentration of A drops to 0.027 molar. And therefore, B plus C plus D is equal to 0.2 minus 0.027. Why is that? Well, the sum of the concentrations of all these four species should be a constant. and in this case the sum should be 0.2 molar. So we're using 0.2 molar minus the concentration of A. We get the sum of BCD, 0.173. And now the ratio between B and C and D is always 2/3/5. Again, we have a ratio among the three rate constants, 2, 3, and 5, and therefore BCD should be 2, 3, and 5. Alright, so now let's distribute this 0.173 molar to B and C and D proportionally. So for B it's just 2 out of 10, for C it's 3 out of 10, for D it's 5 out of 10. And then we get all these numbers for B, C, and D. When time approaches infinity, of course A is completely consumed, A is 0, then B plus C plus D is 0.2. So all of A has been converted to either B or C or D. But how much? Again, let's look at the ratio. B over C over D is equal to 2/3/5. And then we can simply solve the equations. We get the concentrations of B as 2/2 plus 3 plus 5 multiplied by this total concentration. We get 0.04 molar. Similarly, we get the concentrations of C and D. We learned the parallel mechanism and worked on one numerical example. Now let's work on this sequential reaction mechanism. In a sequential reaction mechanism, 2 plus reactions proceed in sequence. So over here, this diagram shows that for A, for the water in A to reach P, it has to pass through this pipe I. Alright, so this is done in order, from A to I first and then from I to P. You cannot go from A to P directly. You have to pass I first. And this is the simplest sequential mechanism, and we can write out the mechanism this way, from A to I and then from I to P. We need some notations for the rate constant, so from A to I, we use k sub A as the rate constant. From I to P, we use k sub I to denote the rate constant. I is considered the intermediate from A to P. Since we have 3 chemical species in the mechanism, we should be able to write out 3 differential equations. Why is that? The concentrations of A and I and P all change with time. So we can have an equation for dA over dt, another equation for di over dt, and a third equation for dP over dt. Now let's look at dA over dt. A is involved in only the first step, from A to I, and it's consumed. Therefore, we have a negative sign here. And how fast is this? Well, the rate is Ka times A. Now let's look at dP. dP over dt is Ki times I, only because P appears in only the second step, from I to P. P is produced, therefore you have a positive expression over here. And how fast is this? Well, it's just K sub I multiplied by I. So we have these 2 equations. Finally, let's look at di over dt in this sequential mechanism. I is produced in the first step, a positive expression. I is consumed in the second step, therefore a negative expression. And you can see the rate of the production of I in the first step is Ka times A. And the consumption rate of I is Ki times I. So you have the 3 differential equations. We're going to assume only A exists at time 0, so I naught is 0, P naught is 0, and therefore A plus I plus P is equal to A naught at all times. Now we're going to solve the first differential equation. It's easy because we have only 2 variables, and this is just the simple first order elementary reaction. We solve it, we get A equals A naught times e to the power of negative KAT. And therefore di over dt is Ka times A minus Ai times I. And now we can replace A with A naught times e to the power of negative Kat. If you look at this equation, we have also only 2 variables, I and T. Alright, but it's not trivial to solve this differential equation. we have some strategies to solve this kind of differential equation. One strategy is to make an educated guess of the expression of I. So I'm making a guess here. I see this exponential function here, so I'm assuming I is a constant times that exponential function. And also, if I delete this part, if I have just di over dt equals negative kii, well, this concentration must contain an exponential function like e to the power of negative kit. So I'm just guessing that I is a linear combination of two different exponential functions, e to the power of negative kat and e to the power of negative kit. Now we plug this into here and here. On the left hand side, we just take the derivative of I this way. On the right hand side, we just express this I in terms of linear combination of these two exponential functions. We can try to simplify this equation because I can see there's a kib times e to the power of negative kit. We have kib e to the power of negative kit. So this to cancel. Now we have only 1, 2, 3 terms, and it contains a, so somehow we can just express a in terms of a naught times ka over ki minus ka. Alright, you can see this exponential function and this exponential function and this exponential function disappears because we can just divide both sides by that exponential function. At least we get the expression of a in here. We're going to try to get the expression of b as well. Again, we took an educated guess. We say I is a linear combination of two exponential functions, e to the power of negative kat and e to the power of negative kit. At time 0, we know the concentration of I is 0. Therefore, we plug in I equals 0 here and time equals 0. And then we get a plus b equals 0. That means b has to be negative a, and b is negative ka over ki minus ka times a naught. And now we finally have the analytical expression of I. We know the expression of a, and we know b is negative a, and then we have this expression for I. I is ka over ki minus ka, and then times the difference between these two exponential functions and then multiply by a naught. We can easily verify that this I is 0 when time is 0, this I is 0 when time is infinity. Let's plug in time equals 0. And then you have e to the power of 0 minus e to the power of 0. That's just 0, and then I is 0. What if time is infinity? Well, you have e to the power of negative infinity minus e to the power of negative infinity. That's still 0. So I is still 0. That's all good. We verified that the expression holds when time equals 0, when time equals infinity. The physical meaning is simple because at the beginning you have only reactant A in the system, so I is 0. And when time approaches infinity, there's only product in the system, so still I is 0. So again, at the beginning of the reaction, I and P are both 0. At the end of the reaction, well, A and I are both 0. There's only P. And in the middle of the reaction, of course, you have a positive concentration of I. That tells us, well, maybe the concentration of I, well, is 0 at first. In the middle, it goes up. And near the end, it decreases until it levels off. Again, we have gotten the analytical expression of I, the intermediate. It looks fairly complex. I is just ka over ki minus ka times the difference between these two exponential functions times a naught. We now do more analysis, especially for two different scenarios. One scenario is what if Ka is much greater than Ki? So Ka is much greater than Ki. You get a negative denominator here, but this is also also negative. So overall, I is still positive. All right. So I has to be either 0 or positive. The concentration cannot be negative. All right. So now let's assume Ka is much greater than Ki. It's one of the several scenarios over here. So what if Ka is much greater than Ki? And then we're gonna just neglect this Ki on the bottom, and we're gonna neglect this e to the power negative Kat over here. All right. Again, Ka is really large. E to the power of negative large number approaches 0. So we get this equation. And of course K and K can cancel, negative sign and negative sign can cancel, so I is equal to a naught times e to the power of negative Ki multiplied by time. Well, what does that mean? Well, this means in this scenario, when K is much greater than Ki, well, A is converted to I really quickly. So this reaction mechanism may be treated just as a simple I to P elementary reaction. Because again, just as long as the reaction starts, all A is gone. There's no A in the system, so it's only I to P. It's only I to P, and the initial concentration of I is just A naught. All right, so that's why we have a simple expression over here. This is just the first order decay of I. What if Ka is less than Ki? This is actually more common. Because later we'll see usually I is fairly energetic, and then K is usually small, Ki is usually big. When that's the case, again, we're going to make approximations. Since Ka is much smaller, we can neglect this. And since Ka is smaller, Ki is larger, this exponential function approaches 0. Now we have the expression of I again. It's equal to Ka over Ki times A. And then in this case, we see, since I is equal to Ka over Ki times A, we can rearrange this equation. We get Ka times A equals Ki times I. What does this mean? Well, Ka times A is the production rate of I. Ki times I is the consumption rate of I. And when this approximation holds, well, somehow di over dt is close to 0, because di over dt is Ka minus Ki, and we're saying this two are about the same if Ka is much smaller than Ki. And we have a approximation here. Di over dt is roughly 0 if Ka is much smaller than Ki. And this is the so-called steady state approximation for I. Well, that's di over dt is approximately 0. That means the change of I, well, is very close to 0. Why is that? Well, if Ka is much smaller than Ki, that means whenever I is produced, it's going to be consumed almost immediately, really quickly. So the concentration of I is always very low during the reaction. The concentration of I is very low in the reaction, then di over dt cannot be large. So I itself is extremely low during the entire reaction. Then di over dt has to be pretty small. And now we have this so-called steady state approximation. Di over dt is approximately 0. And this approximation can be made for unstable, energetic, intermediate species. What if AI and Ka and Ki are exactly the same? And then we're going to use just K to denote both rate constants. This is extremely rare because usually different elementary reactions have just different reaction rate constant. But what if this indeed happens? Well, then we have to solve the differential equation slightly differently. It's going to be this, and then the solution is this. I is Kt times A naught times e to the power of negative Kt. We can still verify this equation is correct when time is 0, when time is infinity. When time is 0, you plug in t equals 0 here, I is 0, and that makes sense. When time is infinity, well, this time approaches infinity, but this e to the power of negative Kt approaches the infinitesimal faster than this t approaching infinity. So this I is still 0, and that again makes sense. When time approaches infinity, there's only P, the product, in the system. There's no A, there's no I in the system. Again, in the sequential reaction mechanism from A to I to P, A is A naught times e to the power of negative kat. This is exponential decay. And if Ka is different from Ki, we can derive the expression of I. And over here, I is a function of time. It is proportional to A naught, and then, well, it's proportional to something more complicated. It's proportional to Ki and inversely proportional to Ki minus Ka. That's proportional to the difference between these two exponential functions. And A plus I plus P is always A naught, so no matter how this water in A flows into I or into P, the total amount of water should be constant. So P is just A naught minus A minus I, and we have the expression of A, we have the expression of I, we put them together. This is a fairly tedious expression of the product. But still, we can verify at time 0, P is 0, at time infinity, P is A naught. Let's plug in T equals 0 here, T equals 0 here, and then you have Ka over K minus Ki over Ki minus Ka. It's going to be negative 1 here, plus 1, that's 0. So P is 0. What if T approaches infinity? Well, it's just this is 0, this is 0, and overall this is 0. 0 plus 1 is 1. 1 times A naught is A naught. So P equals A naught when time approaches infinity. Now, this is extremely rare. What if Ka equals Ki? Well, we're going to just use K to denote both Ka and Ki. We have this equation, and we can rewrite this equation to here because A is A naught times e to the power of negative kt. And we can solve this equation. A is kt A naught e to the power of negative kt. And P is simply A naught minus A minus I. Alright, so this expression is simply A naught minus A and minus I. Again, we can verify this P is 0. When time is 0, just plug in time equals 0 here and here. You get 1 minus 1 minus 0. That's just 0. When time approaches infinity, these two terms become infinity. So P is equal to A naught. And that also makes sense. As time approaches infinity, we have only P in the system. There's no A, no I, it's just P. And P equals A naught. In a sequential reaction mechanism from A to I to P, we have the expression of I. As we verified before, at the beginning, when T is 0, I is 0. When T is infinity, at the end, I is also 0. That means I is likely increasing and then decreasing as the reaction proceeds. I very likely will have to reach a maximum during the reaction. So how do we theoretically derive when this concentration of I reaches maximum? Well, at the maximum, we know the slope is 0, so we set di over dt to be 0. So the derivative of this expression of I with respect to time should be 0. And now we're going to clean up this equation. A naught does not depend on time. Ka does not depend on time. Ki minus Ka does not depend on time. So we can simplify this way. And then we can take the derivative of these two terms. We get Ka times e to the power of negative Kat equals Ki times e to the power of negative Kit. We take the logarithm of both sides and rearrange. We have the expression of the time when I reaches maximum. It's the difference between the logarithms of Ka and Ki, and also divided by the difference between Ka and Ki. So at time like this, both I and Ki reach the maximum. And Ki is just dP over dt. That means the production rate of P reaches the maximum when time equals this, ln K minus ln Ki over K minus Ki. This is when I reaches the maximum. This is when Kii reaches the maximum. Therefore, it's also when Kp over dP over dt reaches the maximum. Again, this is rare to have Ka equals Ki. It almost never happens, but if it does, I'm using K to denote Ka and Ki. And we can solve the differential equation to get I is equal to Kt times A naught times e to the power negative Kt. And again, we can find the maximum of this by setting its first derivative with respect to time to 0, and then we solve this equation. We get this equation, and this equation is really easy to solve. When kt equals 1, this is 0. So both I and ki reach the maximum when the reaction time is equal to 1 over k. And when I and ki reach the maximum, of course dp over dt also reaches the maximum. We have the largest reaction rate expressed as the production of P. Now let's look at one numerical example problem, 13.1.2. In this sequential reaction mechanism from A to I, from I to P, we have two rate constant. K sub A is 0.001, extremely slow. Ki is 300 per second, extremely fast. Let's have the initial concentration of A, which is 0.2 molar. We'll calculate A and P when time is 200 seconds. And we're going to estimate I at also 200 seconds. We'll calculate AI and P when time approaches infinity. So first, at time 200 seconds, A is A naught times e to the power of KAT. We're just plugging all the values. We get 0.164 molar. That's the concentration of A at 200 seconds. I is much smaller than A and P because I, well, if you look at this, the production rate of I is extremely slow. The consumption rate of I is extremely fast. These two numbers differ by 300,000. So once I is produced, it's immediately consumed. And now we're going to use the steady state approximation. That means di over dt is just 0, and that means the consumption rate of I equals the production rate of I. The production rate of I is Kaa, the consumption rate is Kii, so we have this equation. Now we can compute the concentration of this I approximately. It's just Ka times A over I. We have Ka over here. We have A over here at 200 seconds. And then we have K sub I over here. Now we get the concentration of the intermediate I at 200 seconds. It's 0.000000546. We have 7 zeros here, so we know the concentration of I is always extremely low. Why it's low? Because the first reaction is slow, the second reaction is fast. So it takes a long time to produce I, and then once I is produced, it's immediately consumed. Therefore, we cannot have a lot of I. The accumulation of I is extremely hard in the system. That's why it's extremely low. And also because of that, we can say di over dt is also approximately 0. Now let's verify or calculate the concentrations of AIP when the time approaches infinity. When the time approaches infinity, of course, A and I are just 0. There's only P in the system, and P is therefore 0.2 molar.